fourth unit, thermal physics. Before entering into the topic, I like to tell a short story. One day, a teacher told his students that today I am going to teach you about quantum physics. Then he asked a question, is this topic easy? Few students said easy and remaining said hard. Why did they say easy or hard before taking the class? Yes, those who know the topic said easy, and those who don't know the topic said hard. So the word known becomes easy and unknown becomes hard. These two words, such as known and unknown, are creating a large difference like easy and hard. Now, I like to ask a question to you. What is the difference between known and unknown? I am repeating the question. What is the difference between known and unknown? I think you are having an excellent answer with your great idea. Compare your answer with my concept. Now see the question. What is the difference between known and unknown? Use the mathematical concept. Like difference is nothing but minus. High value minus low value. Here, unknown minus known. We can split that unknown word into two parts, un plus known. So the difference is unknown is nothing but un plus known minus known. Mathematically, we can cancel these two known words. Finally, the answer is un. See the answer un contains two letters. One is U, another one is N. Take the small form of these two letters, U and N. Now we can apply the physics concept. If you are rotating the first letter U by 180 degree, you will get the next letter N. Similarly, the inverted image of the U is N. Also, if you take the mirror reflection from the top, you will get the N. So, U and N are interlinked. Now, if you are placing this second letter N above the first letter U, you will get the numeric, first number of numeric 0. As per the Max concept, the position of 0 is very important. If it is left hand side of any number, meaningless. If it is right hand side of any number, great meaning. Here, in that unknown word, by the combination of U and N, the 0 is in the left hand side of known. So this 0 is invalid. Finally, the word is known. Now we can easily convert that unknown word into known with the help of only one small process, combine U and N. Now we can see the meaning of U and N. Let U represent students, N represent staff member. Combination of student and staff, we can easily convert the unknown word into known. So the moral of the story is very simple. You can convert the unknown into the known by working together with the staff member to gain knowledge. I think now my students are willing to work together with me to gain knowledge through this online session. On this note, I welcome all my students in the 4th unit topic, thermal physics. Now see the title, thermal physics. Here the second word is common word, physics. We all know that physics deals with the study of nature. One among them is heat. What is heat? We know heat is a form of energy. This energy is nothing but heat energy or thermal energy. Students, if you touch any object by your hand, what do you feel? Yes, you feel hot or cold. Do you know why you are feeling hot or cold? As per physics concept, heat energy stored in an object makes it hot or cold. Also, we know that heat energy can move easily from hot object to cold object. To study further about the transfer of heat energy, we must know the meaning of two important words such as system and surrounding. Now, system is a part of universe being studied, and surroundings are the rest of universe that interacts with the system. I can explain these two words like system and surrounding with one small incident. We know that this is the pen. Now we are going to study the properties of this pen. Because of this purpose, we can use the name like system. So pen is nothing but system. With that definition, like is a part of universe. Yes, pen is a part of universe being studied. Yes, we are going to study the properties of pen. Therefore, now the pen is called system. Then see the surrounding. Surroundings are the rest of universe. So other than pen, available in the universe is surrounding under one condition that interacts with the system. Here this is a pen. I am holding the pen with my fingers. So the fingers are touching the pen. Indirectly we can say fingers are interacting with the pen. So these two fingers are called surrounding. Similarly, air particles are touching the outer surface of the pen. So air medium is also called surrounding. With this example, we can say pen is a system and fingers and surrounding air medium are called surroundings. I think you got clear idea about the system and surrounding. Now, we can classify the system into three, like open system, closed system, and isolated system based on the transfer of energy and matter. Energy is nothing but heat energy. Matter, anything, any objects in that universe is a matter. First see the first system, open system. Open system is a system that freely exchanges energy and matter with its surroundings. So freely exchanges both energy and matter. The best example for this open system is open vessel. In our kitchen, we are having that silver vessel. If it is in open form, we can consider that is the open system. Now see the picture. There one vessel is there. Actually, there is no lid. Therefore, this is called open vessel. And see the definition. Freely exchanges energy and matter. Here, we can add or remove that food items or any water particle easily in that open vessel. Therefore, transfer of matter is possible. Then see the transfer of energy. If you are placing this vessel on the stove, heat energy is transferred into the food item. So after some time, if you are touching the food item, you will feel hot. Similarly, if you are placing your fingers outside the vessel, that air particles also will be hot. So transfer of energy is possible with this open vessel. Therefore, this open vessel is called open system. Next, closed system. It is a system that exchanges only energy with its surrounding. So transfer of energy only possible. Transfer of matter is not possible. Therefore, here the best example is a closed vessel. So we have to close the open vessel by lid. Now we can't add or remove any food items. Therefore, transfer of matter is not possible. Now see the transfer of energy. After some time, if you are touching the food particles, definitely the temperature will be more. Similarly, if you are touching the outer surface, it will be hot. Therefore, transfer of energy is possible. Transfer of matter is not possible. Therefore, the closed vessel is called closed system. Now see the third one, isolated system. Is a system that does not exchange energy and matter with its surrounding. Just opposite of the open system. Here the best example is hot bag or hot box. If you are placing any hot food items inside that hot box, it won't be transferred to outside. All the sides are completely covered. Therefore, there is no chance for the transfer of matter. We can't add or remove. Similarly, that energy, heat energy won't be transferred. Therefore, transfer of energy is also not possible. Now we can say this hot box is the best example for the isolated system. Next, see the law of thermodynamics. Here we are seeing the first law of thermodynamics only. Reason is most of the places we are using this law. Also in our syllabus we are having the first law of thermodynamics. Now this first law of thermodynamics is related with the law of conservation of energy. It states that total energy of an isolated system is constant. Energy can't be created or destroyed, but can be transferred from one form to another. I can explain this first law with the help of one small experiment. Now, two diagrams are there. One is before heating, another one is after heating. For this, first we have to take one cylinder with movable piston. Here, the bottom side of the cylinder is made by the conductor, and other side like walls and the movable pistons are made by insulating material. And inside this cylinder, we have to take small quantity of gas. Initially, the temperature of the gas is nothing but room temperature. At this room temperature, gas molecules are having some energy. That energy is called internal energy. Let Ui be the internal energy of the gas molecules at room temperature. Now, we have to apply the heat with the help of the burner from the bottom of the cylinder. Now, this heat energy is entering inside the cylinder, and the gas molecules are absorbing the heat energy. Because of this absorption, internal energy of the gas molecules are increasing. Once that internal energy increases, we can measure that value like UF. Q is the quantity of heat applied to the gas, and UF is the final internal energy of the gas. So change in internal energy, del U is difference between these two energies. As the internal energy of the gas increases, motion of the gas also increases. So the pressure is created inside the cylinder. This pressure tends to push the piston upward. So volume is increasing and the piston is moving upward. Now we can say work is done by the gas molecules. So that work done is W. Here applied heat is used in two ways. One is raising internal energy of the gas. Another one is work done by the gas. So the applied energy Q is equal to del U plus W. Nothing but del U equal to Q minus W. That's the first law of thermodynamics. Now see the next topic, thermal expansion. If you are applying the heat energy, that molecules are absorbing that heat energy. Therefore, we are getting the expansion. Now here, expansion is possible along the lengthwise or length and breadthwise or length, breadth and heightwise like volume. Therefore, if we heat or cool a body, it changes its dimension, like change in length or change in area or change in volume are possible. Because of this change in dimension, we are getting the strain. So strain is nothing but change in dimension by original dimension. Here, the strain is produced because of the change in temperature only. Therefore, strain is directly proportional to change in temperature. Equate this with one constant alpha. Alpha is the constant of proportionality, also called coefficient of thermal expansion. Thermal expansion occurs in solid, liquid and gas. Now first let's see the solid. Thermal expansion in solid. Now see these two figures. One, that is the first figure is at cold condition. That is low temperature. Next one is with the high temperature. If you are applying the heat energy, first the molecules are absorbing this heat energy. During that time, we are getting two changes. One is distance between the gas molecules increasing. Another one is movement, like vibration. In solid, that's a vibration only possible. So vibration of the molecule is increasing. But the size of the molecule won't change. So that is very important. If you are applying the heat, the size of the molecule won't change. But we are getting two changes. One is space between the molecules increasing. Another one is vibration of the molecule is also increasing. Then if you are reducing the temperature, reverse one. Space decreases. Similarly, vibration also decreases. Now, based on this shape of the body, we can classify this thermal expansion in solid in three categories: linear thermal expansion, area thermal expansion, and volume thermal expansion. First, see the linear thermal expansion. Here the object is a thin metal rod. That means length is very, very high when you are comparing with the breadth or height or diameter. Here we are having the circular form of that rod. Therefore, we are having the diameter. So the diameter is very, very low when you compare with the length. So here we are getting the change in length only. Other directions are very low and negligible. Therefore, this change in length creates a strain called linear strain. So linear strain is change in length by original length, nothing but del L by L. This linear strain is produced because of change in temperature. So make it directly proportional and introduce one constant like alpha L, nothing but coefficient of linear thermal expansion. So del L by L is alpha L into del T. Now coefficient of thermal expansion alpha L is del L by L by del T. We can define this alpha L with the help of two conditions. One is the length must be 1 meter and change in temperature must be 1 Kelvin. Under these two conditions, alpha L is nothing but del L. So coefficient of thermal expansion is the increase in length of unit length of the solid when its temperature is raised by 1 Kelvin. Now see the area. This is also similar to the previous one, but here the shape of the object is not thin rod, thin metal plate. So here two sides are reasonable, length and breadth. Height is very, very low. So along this height, expansion is negligible. So we are getting the expansion along the length and breadth, nothing but area. So area strain is change in area by original area. Then make it directly proportional. Introduce one constant alpha A, area, coefficient of area thermal expansion. Now we can define this alpha A with the help of same parameters like here. A must be unit and del T is also 1 Kelvin. Now coefficient of area thermal expansion is the increase in area of unit area of the solid when its temperature is raised by 1 Kelvin. Now see the volume. Here the object is in the form of thin metal cube. Length, breadth and height are reasonable. Therefore we are getting the changes in all directions. Finally we are getting change in volume. So volume strain is produced with the help of change in volume by original volume. We can easily calculate it. Now that constant is alpha B, nothing but coefficient of volume thermal expansion. Using this formula, alpha V is the increase in volume of unit volume of the solid when its temperature is raised by 1 Kelvin. So linear, area and volume all are having the similar process and steps, but only one change is shape. Thin metal rod, thin metal plate, thin metal cube. Now see the next content, thermal expansion in liquid. We know that liquids have no definite shape and they take the shape of the container. Here also, if you are applying the heat, we are getting the expansion. Here, we are having one small experiment. Take the conical flask. Best thing is glass conical flask, and that mouth is closed by cork, and insert one capillary tube inside at the center of the mouth, and take the colored solution inside the conical flask till the middle of the capillary tube, and note that level of the liquid, that is L1. So L1 is the initial level of the liquid. At that time volume is also available like V1. Then apply the heat energy with the help of the burner. Here this heat energy won't transfer to the liquid directly. In between these two, we are having one more medium, that is the conical flask. Conical flask is made by the solid material. So here, first that heat energy is absorbed by the solid material, then only liquid particle. So in this experiment, we are having two types of that expansions. One is expansion of solid material, another one is expansion of the liquid. First consider the solid material. Because of the expansion of solid, the internal volume of the conical flask is increased. Because of this increase in volume, the colored solution liquid level is decreases from L1 to L2. After that, heat energies are absorbed by the liquid particle. During this time, liquid molecules absorb more energy and move more vigorously. Reason is the liquid molecules are loosely bounded with other. Therefore, movement of the molecules overcome the force of attraction between the molecule, allowing them to move freely. Thus, the volume or level of the liquid increases up to the level L3. So, L1 is the initial level of the liquid, L2 is the level of the liquid with the expansion of solid only, L3 is the level of the liquid with the expansion solid and liquid. Now, see the change in volume. General formula, change in volume. Normally length into breadth into height. Here, the tube is capillary. Therefore, area of cross section of that capillary tube is pi r squared, where r is the radius of the capillary tube. And change in length of that liquid level is del L. So here we are having two types of the expansion. One is apparent, and one is real or absolute. Reason is, initially we are getting the expansion of the solid only, then only the liquid. Therefore, we are having two types of the expansion. First, apparent expansion. The expansion of the liquid apparently absorbed without considering the expansion of the container. If you are not considering the expansion of container, that means initial level is L1, final level is L3. If you are taking these two levels, that must be apparent. During that time, we are getting the apparent volume only. Therefore, change in apparent volume is del VA, nothing but pi r squared del LA. That is pi r squared into L3 minus L1. Similarly, real or absolute expansion, here we have to consider both expansion of solid and that liquid. Therefore, like L2 to L3. So, change in real volume is del VR, that is pi r squared del LR, nothing but pi r squared L3 minus L2. Here, we can use that strain formula. Apparent strain is available on the left hand side and real strain available on the right hand side. Procedures are same, small change like real and apparent only. Now, change in apparent volume by initial volume. Here, change in real volume by initial volume. Now, see the formulas. Del VA by V1, here del VR by V1. Initial volume is same, V1, V1. Only one change in apparent volume and real volume, corresponding formulas. Then apparent strain is directly proportional to change in temperature. Similarly, real strain is also directly proportional to change in temperature. Introduce the constant of proportionality like gamma A and gamma R, coefficient of apparent thermal expansion and coefficient of real thermal expansion. Using that formula, finally we can define these two coefficients with the help of the assumption initial volume is unit and change in temperature is also unit. So, coefficient of apparent thermal expansion is the increase in apparent volume of unit volume of the liquid when its temperature is raised by 1 Kelvin. Similarly, the coefficient of real thermal expansion is gamma R is the increase in real volume of unit volume of the liquid when its temperature is raised by 1 Kelvin. Now see the next topic, expansion joint, nothing but movement joint. Here, if you are joining any two material, normally we used to apply the paste or with the help of the screw or nut and bolt, like that way we are using it. Here, expansion joint, this expansion is related with the thermal expansion. Normally, if you are using the metal rods, we are getting the thermal expansion of that particular metal rods during the summer. Similarly, during the winter, we are getting contrast. Therefore, that space is varying during the summer and winter. Now we can define this expansion joint is a device, nothing but mid-structure separation. So between two structures, we are having the space. That space is occupied by some material, that's a joint. We are using the word is expansion joint. They are designed to absorb stress caused by thermal expansion or contraction due to thermal changes. Also, it absorbs vibration, hold parts together, allow movement due to earthquake. We are using these expansion joints in buildings, bridges, piping system, railway tracks, etc. Now see the diagram. Here we are having two metal rods, metal rod 1 and metal rod 2. Nothing but the railway track. Here we are having the space between these two is greater than del L1 plus del L2. Del L1 and del L2, nothing but the change in length with the help of the temperature we are observing. Therefore, we have to provide the space between two metal rods must be greater than the addition of these two and apply the some other material like joint material in between these two, fill this gap. Finally, we can connect these two rods without any problem with the strain produced by the change in temperature. Now see the example, like here, the first diagram is we are joined the two metal pipes. Two metal pipes are having the thermal expansion like change in lengths. Finally, that gap is filled by the rubber material. So during the expansion and contraction, this rubber can adjust the distance. Therefore, we can join two metal pipes with the help of this joint like rubber expansion joint. Similarly, here bridge. Normally, you can observe the joints are available in the bridges. So here, that gap should be filled by suitable materials. Like rubber is also suitable for the frequently. We have to change that rubber. Then floor, normal floors also we can join with the help of this expansion joint. Then in the railway tracks, here see the diagram that joints are not in a sharp way, like linearly, just like that knife shape, we have to make it and combine these two so that between these two joints, the gap is less. Normally, expansion is possible along the lengthwise only. Therefore, in that lengthwise, we are having that gap. But the breadth side gap is very low. Therefore, there is no problem the running of the train along this joint. Now see the last topic of this session is bimetallic strip. Here, bimetallic strip, that is two metal strips. With the help of the two metal strips, we are having that device. So it is used to convert a temperature change into mechanical displacement. So here we are getting the mechanical displacement. That means during the thermal expansion, we are getting linear changes, mostly del L. We are using that del L in that useful way. So this bimetallic strip consists of two strips of different metal. Not the same metal, different metal. If it is a different metal, their coefficient of thermal expansions are different. If you are applying same temperature, one material can expand more length, then another one is short one. Therefore, here we have to take two different metal strips and join these two with the help of any join together throughout the length by best thing is welding or paste or riveting, anyone. Now, see the condition, the metal with the higher coefficient of thermal expansion is on the outer surface of the cover. Now see the diagram. We have chosen copper, iron. Similarly here, brass and steel. Two examples are there. In the left hand side, we are having the copper and iron. Initially, both are in the separated position. At that room temperature condition, we are having the same length of the rod. That is true, copper and iron, if it is in the separated position. During this heating process, we are getting the change in length, that is del X. Here, the red color one, like copper, is having more expansion like del X, and that iron expansion is very less. Then in the third one is bounded. If you are joining these two strips, we are getting the bimetallic strip. During that time, we are getting the change. Like the expansion is not in the change in length, like curved one. That means this expansion, thermal expansion, leads the bending of the metal strip. If it is climbed at one end, definitely that expansion is nothing but a cantilever part. Here also we are getting the displacement like along the y-axis del y. Then if you are reducing the temperature, you can see the right hand side diagram like brass and steel. The center diagram is heating. During the heating, we are getting one curve. Like during that curve, the outer surface is the brass. This brass is having greater coefficient of thermal expansion. Then in the last diagram is a cooling one. During the cooling time, that greater expansion must be inside the curve. So this is the bimetallic strip. Here, see the example, bimetallic thermos. We can connect two wires with the help of this bimetallic strip. Like here, left hand side is the incoming wire and right hand side is the outgoing wire. In between, we are having bimetallic strip. Initially, the temperature is room temperature. At that room temperature, that strip must be linear. Then, if the temperature increases, we are getting the bending of the cantilever. The reason is one end is fixed, other end is free. Therefore, it can bend just like a cantilever. During the cantilever position, we can't get that contact. At that time, that circuit should be cut off, so that we can control the current flowing through this circuit with the help of the temperature. Now, bimetallic fire alarm is also available for this case. Here, we are having the bimetallic strip in this circuit. In this diagram, initially, that is in linear position. If it is linear, there is no contact with that lead. Then, if any fire or if any temperature is increased in our room, definitely this bimetallic strip will bend. During the bending time, like cantilever position, it can contact with the lead. At that time, we are getting the current flowing through the circuit so that we can get the alarm from that electric bulb. So with the help of this, we can use the bimetallic strip. Similarly, one more example is also possible, bimetallic thermometer. Now see the diagram. Here, that vertical rod, that is vertical cylinder is there. Inside that vertical cylinder, we are having bimetallic strip. Here the strip is not linear, spiral. So this spiral is also creating the twist of that rod. Actually, above this bimetallic strip, we are having one linear rod. At the top of the rod, one needle is there. The needle will show the temperature. Now see the second diagram. During the heat time, the temperature is increasing. At that time, bimetallic strip got that expansion. Here, we are getting the twisting. Reason is that strip is in the form of spiral. Therefore, we are getting twist. Now that rod got the twist. Because of that, one needle is also twisted. Finally, it can display the temperature of the room or that situation. With the help of these, we can apply that bimetallic strip in many places. Okay. Students, I hope that you have learned today's topic without any pain.